Hi, how are you? Good.
Hi, doing well. How are you?
Good. Okay. Luke, do you know if everybody's in? I don't remember how many of us were there earlier.
Uh, I don't remember exactly how many, but you have 12 right now in the meeting, so I think everyone looks like they're back.
Okay. Okay. And we are still recording, right?
Yes.
Yeah. Okay, so I'm going to get back. And so basically, you go to SAS. You're going to then go with import SAS data. There are many options, as I call. This is the window that opens out. Then you need to select a folder where you have your data, which I have done, and that will cause all the data to show up, right? But really, the data we need is just the not the PDFs and all. So I go to that data. Then you need to decide what columns to load it into, like Q, intensity, and error. For that, you need to click on test and then do that. And I think you can read all this to figure out if you need them, but usually I don't change those options here. And then, of course, I clicked on select all to select all these, um, and also changed to calibration because our data was calibrated. That's it. And then I don't do any changes here and import. So you can see it's imported. Um, the next step is once it's imported, we need to go to, I'm sorry, I was a bit fast there, manipulation, and that's for one or two data sets, data manipulation one. These things I haven't needed to use them, but probably you could explore those if needed. Jan keeps putting in newer and newer features, and unless you need it, you don't get to that. The next thing is these are all QRS columns. That's why you need to click on that, and then you choose some curve, plot it. Um, hmm, sorry, plot it. That's add data and graph. And the second one is just a straight line. The first one is, okay, so that's not what I want. So I go to equatorial and again, plot it. This is already subtracted. Okay, maybe this is the one. Hmm. Interesting. I thought I had data. Um, 1 second. Where is it gone? Where is it gone? Hmm. Oh, I got it. Those are DAT files. That's why. There you go. Okay, so load them again. Um, the ones which are just wedge 0, wedge 1, wedge 0 after subtraction, wedge 0 before subtraction. So I'm going to go with the wedge 0 and plot that. Now you can see this is not subtracted. In fact, if I plot even the wedge 1, you can see that they both match. This is the curve, raw data curve we get. But to subtract, you're going to subtract to a solvent or to a constant background. And I don't have the solvent handy, so I'm going to do with constant background. And this one I don't, for the second data, we just don't select any data. Then you're going to be subtract with a constant background. And you can scale that background over here. That's the modified data to a value here. So to figure that out, I take a cursor, put it in the high Q roughly. That's about 0.1175. I take this. Oh, that's at 1, so shouldn't matter. So I just multiply into 0.11, let's say. Right, that brings us close. You can see over here. So now I just do data 1 minus data 2. These are the operations here. So that's where you select the first curve, second curve, then you plot it. Then this is where you can modify the first and the second data. Once you have done that, then you can do operations of either addition, subtraction, multiply, whatever you want. You can see over here. What we want is data 1 minus some background constant. Once you have selected that, there are other options here which I don't need, but if you need, I click on go always first, because that will create a curve and give me an idea how it is. You can see that this curve sort of levels off still here. So I'm thinking there may be a little more background. So I bring it up to 115. And again, now you can start seeing some background, some kind of a slope that's straight. Now it's possible this is still not perfect, but let's go with that for now. Okay, then we have subtracted the curve. This is the equatorial, which has a strong signal. Now we go to model, and again, QRS. And the first thing is to pick out this data. So, sorry, we go back to the data that which is the 0 wedge. And then once you go select that folder, you now need to go into that and choose the modified one, where the modified curve is the subtracted curve. That's why. Then the first, once you have done that, then the next thing is to select the data controls, add data. So there's only the data which is over here gets saved as under data controls. And here we are only using one. We're not doing multiple data sets. We could actually fit multiple data sets also if required. But there are some constraints you need to keep in mind. Okay, next is to choose your Q. So Q range. So I'm going to say here, we could also be in the first one. And then take that to the last, let's say over here right now. Now, once I do that, the first step is, okay, is my data correct? Yes, it's all scaled by 1. I'm using user errors. I'm not doing the square root of errors or percentage of that errors. I scale it by 1. Then we have to select the Q range. Right now, the Q range is entire. If you did choose a different, let's say you wanted to only fit till there and this till here, then you could then say Q from cursors, and that will get updated. And it will not fit these spots. Okay. For now, I'm just going to fit the entire thing, let's say. So Q from cursors takes the entire thing. Right now, we are not going to fit any background. We can always come back to do that. Then we go to model. Under models, there are many different populations you can have. So let's go with the first population as, I'm going to say I want to use the first population. So I clicked on use. And now it gives you options of choosing between size distributions, unified fit, under diffraction peak or mass fractal, surface fractal. So the first thing is to fit, let's say this is the cylinder here. So we want to fit some kind of a cylinder function here. So I bring my cursor back there, and well, we don't need to, because we can just plot it and see how it looks. The first thing I do is I say, okay, 50 points is less. I want more. I'm going to put 200. I leave that as 0.01 for the tail. Auto distribution. Our distribution is auto. Yeah, I want it to be auto. I don't want to manually decide on those. It generates that from these information that I've given, and I want it to be log distribution. Right now, I'm going to do log normal. We could even do show. These are asymmetric distributions. That is symmetric distribution. What it's saying is, oh, the radius of the cylinder or a sphere, whatever particle shape you use here, is not homogeneous. That means it's not monodisperse. And that's what we expect in a planned cell wall. So I go to the cylinder and say, okay, the length of the cylinder probably is pretty long that I don't see. So I'm not going to fit it. I'm just going to force it to be that. And now I want to calculate this model. But before that, I'm going to select log normal. And, the RG, this is the cross-sectional radius shoulder part. That's about 0.2. So quick one would be inverse of 0.2. And that's 5, right? So I would put something like 10, let's say, or even 8. And the lowest is 3.05, and standard deviation is about 0.5. It's a dilute system. Contrast it's the squared term of the contrast. So it's between any, let's say, the polymer is very similar to protein. So that's at 40%, 100%, because it's 100% D2O. That ratio is about 6, it's 4, so it's about 16. So these are numbers you need to calculate for your system, and then you can fix it roughly. Okay, so now I want to calculate this and show where. So that's where your length of your cylinder, that's the shoulder of your cylinder, but it'll be changed a bit. So 8 means it's actually 8 plus 3, because minimum is 3. So let's say 5 plus 3, that's 8, and then calculate. So see, it's moved down there. Okay, so now we want to fit that part. So we're going to fit that. I'm going to leave the minimum fixed, and I want to vary that too. Okay, that's for this high Q region. Then we need something over here, and we see a shoulder, we see a power law. So I'm going to take, I could have taken a surface fractal, sorry, a mass fractal or surface fractal. But mass fractal would mean I would not get this size up here. Whereas if I take a surface fractal, then I would get the size, and so I'm going to take a surface fractal. Now the surface fractal over here means the smoothness is basically telling you the scaling up and down. The fractal dimension here tells you the slope. That means this slope here. Right now I'm leaving it at 2.5. This dimension is basically 6 minus whatever number you are from the exponent. And the correlation length of 500 is where this straight slope levels off. So right now, 500 angstroms is pretty less. So I'm going to make it 2000, let's say, and then see what happens. And then again, I say, yeah, the contrast is still 6, and calculate this. See, it goes up, but because we are adding the 2, it's difficult to gauge. So I'm going to remove this fellow and only see. Now calculate. So now you see you're only sensitive to this part. It sort of gives you there, but maybe 2000 is too much. So 12. Oh, if you click on this right below the blue line here, auto recalculate, then I don't need to keep pressing calculate. So calculate automatically. So you can see it's sort of leveling off here. We can try that, but we need to move it up a bit. So 3,500. No. How about 7,500? There you go. And this, you would need the slope to come down a bit more. Yeah. So you need to make it 6 minus maybe 2.1. Let's try. Yeah. So that will have to come down a bit. So you can see I'm playing around with these numbers to get it close by. It doesn't have to match perfectly, just close by. And okay, so let's make that 50. I want the curvature, and I need to go up again. So I play with it. So I just want to capture as much as I can. And it's possible I may not capture it well, but then I add it with this. And now you can see, okay, there's some resolution. Now it's not perfect, right? But we're going to try to fit this and see what happens. Before you fit, always check your fitting parameters, the range. It's usually it automatically populates such a way the value you put is within this range. Yes, all of them are. Now I'm going to say I want to fit the intensity. I want to fit this. I also want to fit the curvature where it should be, and these. Okay, now fit all of them to see what we get. Okay. Okay, so you can see that the cylinder form factor is showing up. You see the cylinder form factor is showing up. It's not actually applying the distribution well, so it's forced the distribution to go much lower. I will let that be for now, but it basically fit this part reasonably well. It did not get this part well. And that could be because the error bars are much larger, so it didn't give as much importance to that part of the fit. Whereas this part, okay, it didn't capture it very well, but it sort of got it. So what are these parameters? This is saying, okay, so basically it went to 2. That means it's saying it's a smooth surface because I did mention 4 is smooth, but if you do 6 minus 2, that's the exponent 4. But the fractal dimension for surface is always 6 minus the exponent, or vice versa. So that is minus 4 would be 2. If this becomes 3, which is the other extreme, then that would be 3, because 6 minus 3 is 3. The other thing is this correlation. So we may want to force this correlation in some way to match, to get there. So 150. It'll come down a bit, but then we fix the correlation and see if it will capture the curvature. And it'll scale it up and capture the curvature. It may not, because then this may not capture. Let's try that. Yeah. So if it's capturing that, it's not getting this power law. That's what's happening. So if I use that, oh, I shouldn't allow that to vary. I'm sorry. Once it's hit its limit, there's, I'm going to put this as that. Yeah. So there's some aspect here that maybe we would do better by fitting with a unified fit, maybe, and then or even a quality dispersed sphere, maybe. But we don't know what it means right now. It's some big, large particle, and these are the cylinders. Because the plant cell wall it's not a single component that has a building block that assemble. There are many, the polymer can be in different ways, and the cellulose can be different. So that's your cylinder part, and that's your larger particles. The larger particles have a smooth surface, and their rough size is closer to 1200 angstroms. At least that's the lower limit, right? And to see the distribution, you can click on that, and that'll give you the distribution. I can remove the red one, and then say from 6. Okay, so now this distribution is basically monodispersed, right? Because it's assuming it's not able to pick up this piece. So let's try Gaussian. Maybe we'll do better with that. 10. And so you can play with different deviation sizes or sorry, distribution functions, and see which one gives you. So you can see that's not as good, but we're going to give it a try and see what we get. No, that also wants to go to, so it's not able to pick that up. That's because we probably have still some solvent there. So the other option is to keep subtracting. The other thing could be, oh, there may be some of the isotropic component, and that could also be giving rise to this. So let's first start. Then we go back to the subtraction, and we say, okay, let's try to subtract this with wedge 1, right? So if you do 1:1 subtract, and I'm going to call it as modify 1 so I don't overlap with the previous data. And then you can see this is far more sharper. And it's possible there was some of the amorphous contribution that's corrupting. So let's save that. That's one option. The other option is to go back and say, okay, it may be just water in current scattering. Let's just try to do a better job. So 0.117, let's say. Oh, I get you. 0.117, and that's even more closer. Now we call that as 2. You see, now we have a much more subtracted curve. A few of these final points have disappeared, but it could become in the negative direction, but that's okay. No, I don't need to change that. I come back here, and now we can try fitting different ones, right? So we need to get out, go to some other folder, come back to this folder, and then you will see these mod 1, mod 2. Mod 1 is when we subtract with isotropic. And now we need to plot this again. So you can see this is a little more sharper. And then I'm going to try fitting go back to the log normal, and I'm going to say that there is no polydispersity, let's say, and then we try to fit this and see what we get. Okay, 0.1 maybe still high. And okay, and then the next thing is over here, I'm not going to change the slope, and let's see what we get. It's struggling. See, you can see it's struggling. So you need to go back and help it a bit. Now, there's also a possibility that there is a structure factor here. So that's another thing. So let's go here and we say, okay, maybe there's a structure factor, and then you can, go back here and you say there could be a structure factor and say interference. Now this interference would be, you want to fit those two, how much, maybe about maybe about one, one, and then the distance should be very similar to the size, so maybe about 20 angstroms, let's say. And then this is too small, should be about 5 at least, or maybe even 8. Yeah, there you go. And now fit this again. And you can see that it's able to do that a bit better. So this is basically how we go. We have to build on it, and okay. So the next thing is fit with a background. There's a background here roughly. So let's say 0.001. There you go. And fit for that too. So let's fit that and then see what we get. So you can see that, everything is, now we are able to fit that a bit better, but then it does show that there's a peak, which possible. Is just we're not resolving the peak, but the form factor suggests there is a peak. May not be right. Okay, so then other option is to do the unified fit instead of surface. So then you remove the surface and you use 1 and 3 now. And you can go to unified level. In the case of unified level, that would mean so what is a unified model? It's basically a Guinea function and a power law function combined together. So the first two terms are for the Guinea, that's the scaling for the Guinea, and the RG, the size of the Guinea. And it should be RG should be about, let's say 100, maybe more, 100 and 300. Okay, and then that should also be a bit high because this is 1,000, whereas the B should be much lower. So that's where we need to get that B down, because that's the power law slope 4. We need to get that down. So I'm going to add 3 more zeros. There you go. Now it's coming down, and RG can go further big. And 9. Now our power law is down here. Power law 4. And that's why. Okay, so we'll have to just play with this is the scalar, so you're playing with moving it up and down. The slope, that's your slope. We know it's roughly 4, so I'm not changing it from 4. Then this is the guinea part, the shoulder. That's your RG, position of your RG, and that's your intensity. And that intensity is up and down, whereas the RG is left and right along your Q axis, right? So right now it's sitting somewhere here. May not be correct, so we'll have to increase it more. See, there it goes. And we need to increase this also, intensity also. There you go. Okay, so now now we'll fit for all these. We fit for the RG, we fit the vertical where it should fall, and then the height of your slope. But I'm going to leave the slope as 4. And we got reasonable fit on this side once we put correlation. Okay, so now you can see that the fit is much better. So when you use the surface fractal, it wasn't able to fit it as well as with the unified fit, with the unified level, combined with cylinder form factor here. But there is something that's happened. The interference seems like it wants to move that up here. And it's hit a limit. So play with that to see why it wants to do that. So maybe there's a feature that's not able to pick. So this is what's happening here. It's trying to fit for this peak here. It's trying to move this peak to fit this part. And so then it's corrupting everything around that. So yeah, probably not going to work that way. So like that, there are, when you do these hierarchical structural fits, because you use many different models that you combine, there's always the tendency for the fit to diverge in the wrong direction. And we need to always bring them back. So what happened? Oh, I guess so I would go back to roughly the size of your cylinder. That's about 10 angstroms. So I would say maybe 20, come back to that, and about 1. This volume fraction of about 5 is like a 5 or 6 is closer to cubic phase order. We are not there because we don't see diffraction peaks. So anywhere between 1 to 2 is all what I would expect for the volume fraction. And so I'm going to force these for now not to vary, and then fit. So it's always, if it's diverging, it's good to fix some of your parameters. You can allow that maybe. I mean, that only how much of it is there, not what is the correlation. And then once you get that, I think this oscillation is going to cause us a problem. So one thing we could do is say that there is a polydispersity of 0.2 or 0.25, and then see, you get rid of this oscillation. It's still there, but it's sort of minimized. And then this structure factor will only try to get the kink. At least that's what I expect. So let's try that. for now, oops, 1 second. For now, I want to keep that fixed. I don't want to vary that too. Okay, so getting to 11 o'clock. So now you see that it's sort of settling down there, but then you say, okay, maybe I cannot determine the distribution of my, well, let's try it anyway. Maybe it will. No, this has hit its limit here. So this has hit its limit because it's forcing that to go. So I would just say there's some degree of polydispersity, and we cannot determine that, but we can say that there is a rough. What is a rough? Let's see. So you see it's between the radius of gyration, or the radius of the cylinder basically goes from about 5 to 25. If you reduce this distribution, you create a little more oscillation, and you'll make this distribution much more narrower. Now, one way is to look at the solvent subtracted, which is much more subtracted from solvent, and see if there is a little more data over here, maybe. If that, so right now it looks like there's very less data, the place where where the oscillation tries to come up. So it's sort of not able to resolve this distribution because of that. So we just need to fix it for now. And then I think this distance may settle down better. Still not able to capture that. It's continuously moving. So we need to play with this a little more to figure out where it catches well. But it's 11 o'clock, so I think now it's good time for people to ask questions for their specific science, rather than me sticking and trying to do these fits here. But I think you understand. You build different populations, you can mix and match, and you could also go and do this with unified fit that is purely unified fit, multiple levels of unified fit. That's each level consists of a Guinier, that's the shoulder, and a power law. Guinier, power law, Guinier, power law, like that. That would be when you want to use multiple levels of unified fit. That's if you use more isotropic patterns, then it's easier to do that. Once you go to anisotropy, usually you sort of select out a specific shape for those strong scattering parts. Okay. I'm going to stop sharing and see what questions people will have on their system that I need to help you with.
Vinky, we had a question. I don't know if I can just share screen and show you kind of what we're working on.
Yeah, you can. Yeah, you can.
Okay, cool. Open share tray. Olivia, do you know how to do this on?
Oh, so there is a white button beside leave. If you go to leave,
Open share.
the red leave, and then
yeah.
Now when you click on share, you get multiple windows.
Right.
The first window, the leftmost top window, that's for the entire desktop. So any application can be seen. Or you look
I think
for
Olivia's going to try to share on hers. Mine isn't showing up for some reason.
Okay. Yeah, this is your SAS view. Is Are you talking or cannot hear you though if you're talking?
Sorry, yes, hello. So we're having a little bit of trouble getting this aligned here. We're using a 2 Lorentzian fit, but also we've been using SASView instead of Igor, and I don't know if
Oh
that
yeah,
is.
that's fine.
That's okay.
Any software is fine. I was just the unified fit or this combination of models I felt was easier to show through um, the unified or Igor Pro. The SAS
Yeah, I
view
think it's
windows are a little more painful to work with. That's why
it is a little painful, but I think I'm not sure
the
if
big
this is
screen.
exactly the right model, but it fit pretty well for a different. We're doing the different durations, and so it fit pretty well for one of them. But we're kind of having
So,
trouble here shifting.
so when you do 2 Lorentzian, um, I need to see the equation for that. If you click on help, it will help for us to
Yeah.
know.
So what we were thinking we might be seeing is in our polymer we have HPNC C12. So we were wondering if like one of the length scales was the C12 and one of them was the like larger polymer construct. And at least the numbers we got from 100D sample worked out really well for like how large we'd expect a persistence length to be for C12 as compared to the other broader polymer. But also, like, we're new to this, so if you have alternative recommendations for fits that we should be considering in scattered.
Yeah. So how would you interpret even if you did Lorentzian and um, you get the get an exponent and sorry, go ahead.
So we have here like the length and an exponent. And so I was thinking that this length here, the 350, is about like a 35 nanometer persistence length of our polymer, which is modified, so it would be hopefully a little bit more stretched out. And the exponent that we have here, I don't know if this 3.53 corresponds to being like a little bit less than smooth, or is that not
Right.
the,
So that's why it's good to see that expression here. If you click on help.
oh yes, help.
Okay, so it's this. Um, is it M and N? The exponents are M and N?
Yes. Mm-hmm.
Yeah, so that'll just be Q power minus M when it comes up. Yeah, that's your exponent. 3.5 would mean negative 3.5, right? So yeah, you could go back to the SAS view. Yeah, so that should be a surface. But what do you get as exponent for the other one? That
For the other one, we're down at 1.4.
Do you want me to do the exponents from my fit
so
for the
1.5
100D since it
is
was a lot better?
yeah, 1.5 is more like a in a good solvent, polymer in a good solvent.
Yeah.
Do you
On the fit
expect?
that generally fit better, our exponent 2 was 2.8.
Mm. So the higher
Because this
Q
fit
was
doesn't seem to be
2.8.
doing a job.
Yeah, so the problem with these exponent fits is you can misinterpret if you did not do proper background subtraction. If you don't know where the background is, then it's sort of difficult to say, because if I keep subtracting, the higher Q will be far more sensitive. Whereas the low Q, the low Q is on this side for on the left side of the curve, background subtraction is not as sensitive. So your slope is pretty well defined. But at high Q, which is on the right side of your curve, you're very close to background. If you cannot determine the background correctly, then it's sort of arbitrary on how well or how much you think is a background and subtract. And that's what would force your exponent. So if you play around and try different amounts of background subtraction and then see what is the range in that exponent, it sort of gives you a idea of what is the reliability of that parameter? To what extent do I know? Can it actually go all the way to -3? If it cannot, well, at least you can say we find that this power law exponent falls between, let's say, 1.3, 1.4, all the way till 2.2 or 2.3, right? So at least it eliminates option of interpretation that's at hyperbranched or the other side where it's rod. -1 would be a rod.
Yeah. So we did various background subtractions, and I'm not sure which is like the most appropriate one. So the one that I'm fitting right now is the blue line. But then we did some more subtractions, and it seemed to fit worse on these because you don't get as nice of like a little plateau there. But yeah, I'm not really sure
So
what's the
so
actual.
the green is the one you fit?
No, the blue is the one that we fit.
Yeah. But the green one seems reasonable, right? Because
Green
you
seems
still have enough. Yeah, because it seems like you still have enough. So when you go to the blue and show in the fit, with the fit one.
when on the blue fit, yeah,
Yeah.
it's this.
Yeah.
I have. Should I fit the green
So
one?
you
I have
can,
that here.
no. I mean, I just want to show, when you look at the fit in the blue one, only the high Q, really high Q, the fit is on the data. Otherwise, you're always fighting to be on the fit. So you're crossing over, right? Which means something is not catching it. Your RG for the second exponent, Laurentian, or your length scale, which is 127. I wonder where that is then.
Yeah, we're not
127
like
is very large.
edit.
No, this is not the right fit, right? Is this the right fit?
Oh, this is the other one. Sorry, we are at this one. The 350 and 1.5.
So is one second. What is your length? Length is just 1 angstrom?
Yeah, we don't think this
I think
is
that one's
correct.
wrong.
Yeah.
So for a different
so you
one,
need,
we got a length of 5.36.
yeah, so that is the issue I face with SASView is you cannot see the individual component of your functions. Whereas in Igor, I'm able to turn on and off and see how the individual parts come together. It sort of gives me a little more confidence. But if there is a single Lorentzian function, what you could do is simply copy those parameters for the Laurentian 2 into that and see how that function shows up. That'll give you a visual idea of where the peak of the Laurentian is, where the slope is coming, because it's basically this Laurentian is coming down like that. It's the curvature of this shoulder. Instead of being an exponential fall, it's sort of stretched fall, right? For a Laurentian, that's what is happening. So if you're doing a peak fit of a Laurentian, you have a peak and it's the way how you come down, right? Same way you're inverting and you're creating that curvature, and you're picking out what is the length and what is the slope of your fall. I like to. You see, you when you click on help, you saw that function, right? If you have a method that you feel comfortable to just write that function somewhere and simulate it, you can do that even in SAS View, right? You can do simulation of models. You go to simulate of models and then just simulate a single Laurentian. You get a feel of what parameters, when you get, let's say, 350 angstroms for length 1, where should that feature be? Is it accessible for me or not? It's just a fit, but it's outside the range I'm actually even fitting. Yeah, one way is, what was your minimum Q, let's say 0.003, and you take inverse of that. That'll give you some idea of where that correlation length is. All right, 350 is at the edge, I would say, because it's inverse of length when you're doing RG.
Yeah.
And 0.003 inverse is about 333. So you're at the edge of that. That's why you can see that the curvature is it's sort of going up, but it's not leveled off. But it's saying 360, it's slightly greater. That's why if you model it and you get a feel how the shape should look, that gives you much confidence. Okay, this makes sense, what I'm fitting. Otherwise, these parameters make sense. Right now, I have a feeling that you're not actually capturing the features, correct positions of those features. And I think the green subtracted curve may be a bit more relevant than this, because I think you have not subtracted enough background. As you go to really high Q, that's closer to the 10 power 0, basically you have only background, usually. It's very rare, even if a polymer is there, the scattering signal from a polymer chain, when you don't have, is difficult to overpower the incoherent scattering from hydrogens, unless you have played with your system so well that you have almost no hydrogens. You see, then you will be able to see, or you have just loaded your sample a lot with polymer, and it's very little solvent, very little. But the polymer has no hydrogens again. It doesn't matter where the hydrogen is coming from. You do have, right? That's why really high Q should be a background. I would definitely do more subtraction of background. That could be a guinea there. So that will tell you a rough size of your individual segments.
Okay.
Within
we could fit a guinea to the
and then
this area.
And the low Q could be your larger domains or aggregates. And within the aggregate, you have smaller building units, and those units are here. It may be cylindrical shape. You could try that.
It could be what?
Cylindrical shape. That means it could be rod, right? Because there seems to be a slope leading up to the point where orange is there. You could test that. You could, when you subtract, you just put a power law 1 and see if the power law 1 matches. That gives you some feel. Okay, maybe it's there.
Mhm.
But
Okay.
um,
Thank you. Yeah. Oh, could
Vicky,
I
can
have
I
you?
add something?
Oh, yeah.
yeah,
So I have fitted these kind of curves. In my experience, for your blue curve, it's very hard to fit into a two Lorentzians. Like Lorentzian function is falling down, right? If it is slightly is going up, then you can capture it for a two Lorentzian. But for your blue curves, I think it's very hard because you have clearly two slopes. So if you want to capture it, you have to have a different function other than the Lorentzian on the top of one Lorentzian. That's my experience. I think the green curve is more reasonable to fit the small angle data too.
Okay. Thank you.
That's
We'll
only my
definitely.
experience.
thank you, Manju. But you said you were able to fit some data, right? With these.
Yes. So Carolyn has the. Do you want to screenshot it and send it to me? And also, could I get you to look for a second at the nanoparticle data that we fit
Okay.
to see if it's reasonable? So this is
Yeah.
one of our fits for the all deuterated. And we get
This
we
is
get
the
these
core shell,
parameters
right?
here.
Yeah.
Yes, this is core shell.
Yeah.
So we have that.
You've fixed the core solvent,
We
but you
fixed the core
allowed the
solvent
shell to vary.
because
Yeah.
we figure that the core is the denser PLA
Yeah.
and has
Yeah.
not allowed solvent.
Okay. Yeah. This looks. Yeah, the fit does look pretty good. Um, do you have? Did we study at other conditions, or this was a
Yes, we have.
single? And did this model of fitting approach work for the other conditions? And yeah,
It did. It varied slightly throughout.
yeah.
So I have.
So one way is to tabulate, when you changed from one condition to the other, how did your fitting parameters vary?
Yeah.
And if they make sense, that's one other way to say I'm doing a simultaneous fit, not really doing it, but using the science to say, okay, it makes sense. The other way is if there is a way to keep some things constant because they could have been constant, then you could simultaneously fit them by making them as a single parameter.
Yeah, we have. So these are a distribution of our fits. And so this is at 100. These are all of our different scales of deuterated water. And I guess these are the things that we're paying attention to mostly.
Oh,
And the contrast match point we found was what, around like 30, 35. And so that would be around this one. This is 10.
yeah. So there's some correlation between the radius and thickness, because of which the overall radius is the overall radius is from your correlation distance. Okay. That hasn't changed. Why? But it's the same nanoparticle though in different contrasts.
Yes.
Okay. Why would we? So are you expecting that much variation in the particle size?
No,
At
it's kind of strange.
I guess
So
we're also not sure since it's made of both PEG and PLA,
right,
how like contrast match points may be
yeah,
different between those polymers.
right. It's possible. So did did I do a calculation for you, or did we calculate for PLA? Some discussion we had. No,
I'm
No.
not
the contrast
sure.
match points. No.
We
We
did do
looked them
contrast
up.
match. And yeah, we've looked them up for PLA and for deuterated water. And then we didn't do anything for the PEG part, but that we're allowing.
Oh, you're
Okay.
saying SLD.
Oh.
The contrast match points, like the
Oh.
percentage.
So one thing is to think if the PLA is outside, and at 100% our PEG is well, PEG should be outside, I guess. But if something, maybe you're not seeing something, and as you're changing the contrast, you're
Yeah.
not seeing the entire particle, and so the shape is. But overall, you still have a thickness of close to 35 to 40 angstroms all the time, shell. So that's it's confusing.
And these fits look like
We need to understand your. I need to remind myself about your system again. I've forgotten. But once the fits are good, it's just yeah.
Yeah, the fits close to the contrast match point are like a little bit worse,
yeah.
but they're not terrible.
Yeah. So, but we need to think about why would the radius be that different? If they are the same particles, why is the radius different? Is it possible that when you're preparing, and you prepared them separately and they can have different sizes? There's not, no, right? There
These
should be.
to achieve the different contrast match points, we just mixed solutions, or not to achieve the different deuterations, we mixed solutions of all deuterated water nanoparticles and undeuerated water nanoparticles. So they have all the same components.
Interesting. I would not have expected. So simultaneous fit, which from Rana Ashkar's group, I forget her name. Yeah, I just showed her how to do the simultaneous fit in SAS View. One option is to try that. Do you know? I mean, if you open SAS View, I can tell you. So if you go up to fitting and constrained and simultaneous fit. No, go up, go up. Yep, there. There's a window that opened on the back. You see, now you can connect. Different. Well, right now it's using the Laurentian, but had you loaded all your fits for the core shell, you could then connect saying that the core radius should be constant among all these curves.
Okay.
The shell thickness should be constant. So you're fitting one curve, you're saying one or any one of them, maybe 100%, whichever has good signal, you say that is your fitting parameter for radius, let's say, right? All the other radius, you should be equal. You should make it point to that radius. So they have become fixed to the radius of 100%, let's say. And if the thickness is also not changing, let's say that also should be there, right? Now, the SLD of your core is fixed. SLD of the solvent is varying. SLD of your shell will vary because you don't know, it should vary based on the amount of solvent, right? Then your fits may not be as good, but at least your comparison from one to the other, you feel more comfortable because then you can see a trend. Right now, 76 angstroms to 115 angstroms, right? 75 to 115, that's about 30, almost Yeah, 30, 25 plus 15. So that's about 40 angstroms.
And I would
variation.
tend to trust these better than the lower ones.
I'm not sure which one you're referring to.
Oh, I would
100%. You feel more confident of the 100%. You're saying?
yes.
Yeah. Yeah. So I would go with some this. Yeah, I think it's better to go that way, and even the um, effective radius, you can point it to any one of them which shows that peak very well, and then link it to that one. And then when you fit it, you're sort of now reducing your number of fitting parameters, but you're keeping the same number of curves that you're fitting. So your fits become more, at least the values of the parameters you get, they become more consistent all across.
Okay, cool. And to do that, would I check batch fit or
Well,
chain? What would I?
I think you could do single fit, but
Single fit. Okay.
but it's single fit, but it's the constraints on the bottom that you have to.
Ah. Okay, very cool.
Yeah,
Yes.
you build the constraints and then you just do a single fit.
Mhm.
Right? When you click on
Yeah.
single fit, but it's really which of the green boxes you have selected.
Mhm.
All those curves will be used in the fitting process simultaneously.
Okay, very cool. Yes, that makes sense. Thank you.
Anybody else? So the other thing is you can, Carolyn, you could use, and Olivia, you can use different kinds of optimizer. Right now it's the Levenberg one. If you go to preference or so analysis, there are other options that may help settle down to a result better or easier. Usually the Levenberg is a good one to start with, but when you want to then do a much better fit, um, Dream is the other option that we use. So
Where would I find that? Sorry.
I think it's in preference that you set it. If you go
Okay.
through this way, um, GPU options, and try that GPU options. No, that's not
No.
correct. Sorry, not GPU options.
Fitting algorithm. Yeah, that one.
Ah,
Yeah,
thank
that's right.
you. Very
Yeah. So you can
So we could
choose
try
different
Dream.
ones. Yeah.
Okay.
Dream is more, um, it's far more time consuming. So you would want to apply something first to get your fits close. So your fit is on the curves, it's not somewhere else. Then if you apply Dream, it'll not take as long as if you apply Dream directly.
Mm. Okay, thank you.
Thank you, Manju. Any other question? It's like okay. If there are no more questions, then we can end the meeting. Are you talking to us?
Oh, yeah. Sorry. If
Carolyn?
no one else has
Yeah.
questions, could we still keep asking you a few things about our data?
Sure.
Thanks.
Anybody else has questions? If not, I
Yeah, if
probably
anyone
will
else
be
has
working
something,
with
they should
Carolyn.
definitely go
And you're
ahead.
welcome to leave if you don't want to, if you're done. So let's call it as end. Bye for all those who want to leave. Thank you very much,
Olivia,
Thanks
Manju
a
can you
and
lot.
pull
It
up
was very helpful.
the
bye.
Well,
You guys
Becky, you want to
screenshot
stop
us
the
in.
recording?
Thank you.
Oh,
Thank you so
yep,
much.
thanks.
You probably don't need to record questions.
Uh,